magnetic field due to a bar magnet. Okay, so this bar magnet, it is actually similar to an electric dipole. If you remember, in electric dipole we have two equal and opposite charges separated by a small distance, okay, 2r. Okay, so this is an electric dipole. Similarly, when you look at a bar magnet, we can treat this bar magnet as an electric dipole. This is because this bar magnet, it consists of two equal and opposite poles, and the magnitude or the strength of each pole in this case, it is the same, but the difference is only the magnitude. Okay, so that is why this bar magnet, it is sometimes known as an as a magnetic dipole. Okay, all right. So now I want to determine the magnetic field due to a bar magnet, let's say at an axial point. Okay, so what is an axial point? An axial point, it is a point which is lying right on the axial line. Okay, so this is a bar magnet which consists of a south pole and north pole, and these two poles, they are separated by a distance 2l, and this is the axial line, okay, which is passing through the two poles. And I want to determine the magnetic field, let's say at this point P, which is a point on the axial line. Okay, so for that, right, I will consider that this point P, let's say it is at a distance small r from the center of the dipole. Okay, and after that, we will also consider that the strength of the south pole in this case is minus qm, and the strength of the north pole, it is qm plus qm. Okay, so in order to determine the magnetic field at this point P, what we have to do here is we have to consider a unit north pole placed at this point P. Okay, just like we consider a unit positive charge placed at this point due to an electric dipole, but in this case we will consider what? A unit north pole. A unit north pole placed at a point P. Okay, so this unit north pole here, it will experience two magnetic forces. The the first force of this unit north pole, it is due to the north pole of the magnet, and the second force at this point P, it is due to the south pole of the magnet. All right, so now let us see how much is the magnetic force due to the south pole of the magnet. So for that, I will write as Fs. Okay, so if you remember in Coulomb's law, the electric force which is experienced by a charge placed at a distance r from its source, it is 1 upon 4 pi epsilon naught, okay, q1 q2 upon r square. Okay, so now similarly, this magnetic force at a point P due to the south pole of a magnet, it can be written as, instead of this constant, I will write mu naught upon 4 pi times q1 q2. What is q1? Your q1, it is minus qm, so I'll just simply write only magnitude, that is qm, and your q2, it is what? A unit north pole. So for that unit north pole, it means the magnitude is 1, so I'll write as 1, okay, upon the square of the distance between them, that means upon r square. All right, okay, now where is the directions of this force Fs? Because F here, it has got a negative, right? Or I can say this south pole we treat as a negative charge and north pole as a positive charge. We can treat in that way. So therefore, the magnetic force at this point P, due to the south pole, because this south pole behave as a negative charge. So, and this north pole behave as a positive charge. So therefore, this force Fs, now it will be attracted towards the south pole. So which means the directions of Fs will be along this side. Okay, so I will write inside bracket, it is directed along PS. Okay. Okay. After this, I will write Fs is equals to, I think I made a mistake here, a little bit mistake. Actually, the distance between the south pole and this point, it is not just R, but it should be SP. Okay. So SP square. Right. So again, right, if you rewrite this equation, then you will get like this. And instead of SP, because SP, half of this length, it means L. So L plus R will be SP. So instead of SP, I'll write R plus L and then whole thing square. So I'll name this as equation 1. Similarly, the magnetic force at this point P, due to this north pole, it is Fm. And this again equals to mu naught upon 4 pi strength of the pole upon square of the distance between this point and this point. So the square of the distance means np square. Or I can say this Fn here, it is equals to mu naught upon 4 pi Qm upon, instead of np, I'll write r minus l whole thing square. This is my equation 2. And what about the directions of this Fn? The directions of this force Fn, it will be actually, like a repulsive force. Because at this point, we consider a unit north pole. So this is a north pole. So the force experienced by this north pole from this north pole will be a repulsive force. And so it is acting along, and I can see here like along NP. Okay. So after you have obtained the magnetic force due to south pole and north pole, then what will be the net force acting at this point P? So the net force acting at a point P, it would be actually equals to, the algebraic sums of the two forces Fs and Fn. Okay. Or in other words, because my aim here is to find out the magnetic field. So the magnetic field at the axial point P, it will be equals to, I will write okay, Fn plus minus Fs. Okay, I hope this is clear, because this Fn and Fs are acting in opposite direction. So therefore, instead of before this Fs, I have to write this minus sign. Okay, now this net magnetic field at a point P, it will becomes how much? Substituting the value of Fn, which is equals to mu naught upon 4 pi Qm upon r minus L whole thing square. And plus times minus will be minus. Instead of Fs, I will write mu naught upon 4 pi Qm upon r plus L whole thing square. Okay. Now, if you further simplify this equation, then you will get the total magnetic field at a point P, right? Looking at these two terms, this mu naught upon 4 pi Qm can be taken common. So I'll take this common, and inside I'll have only 1 upon r minus L whole thing square minus 1 upon r plus L whole thing square, and then, right, this is the external bracket. Or this B axial here, okay, it is equals to mu naught upon 4 pi Qm. Now find out the LCM here. It is r minus L whole thing square times r plus L whole thing square. And cross multiply, you'll get r plus L whole thing square minus r minus l whole thing square. Okay, right. So, right, for the expansion of this equation, I need a larger space, so that is why I have to rub the above equations, right? And if you want to look at these equations before, you can just take a screenshot, right, on your mobile phone. Okay, now let me expand this b axial. Okay, applying a formula a plus b whole thing square, you'll get a square plus b square plus 2ab. Minus, similarly, applying a formula a minus b whole thing square over here, you will get a square plus b square minus 2ab. But this is the bracket. And next, in the denominator, I'll write r minus l, r plus l. Okay, and then I will take command the square from here, I'll take command. Okay, like this. Sorry, I'll take it like this. Okay, square. Okay, now this b axial, right, in the next step it becomes like this. If you remove this bracket, then the sign inside the bracket, right, will change, which means this will become minus, this will become minus, this will become plus. So what we see here is that this minus r square with this cancel, l square plus l square minus cancel. So you'll be having in the numerator only 2rl plus 2rl mean 4rl, and in the denominator this is a minus b, a plus b, it means a square minus b square, and with this square outside the bracket. Okay, so this is okay. Or I will extend this one more steps, like q naught upon 4 pi. Okay, now I'll write like qm times 2l, okay, with a factor 2 here, and then times, r upon r square minus l square whole thing square. Okay, I hope this is clear, because it's nothing but I'm just splitting the terms. Okay, so if you look at the numerator, we have mu naught upon 4 pi, so this is the thing. 2 times 2 mean you get 4, qm is this, and then rl is this one. Okay, so why do I'm writing like this? I'm writing like this because there is a meaning, because in place of qm times 2l, the product of any charge and the distance between them, any charge and the distance between them, it is what? Magnetic dipole moment, and for that we usually denote it by the letter small m. So instead of this, I'll write m and then r upon r square minus l square whole thing square. Okay, all right. How much is m here? M is equals to qm times 2l, and this is known as magnetic dipole moment. Okay, now for a short magnetic dipole, or I can say for a short bar magnet. So when this magnet is very small, then what happened at that time is that this L, which is half of the length of this magnet, it will be, very small compared to this R. So therefore, when you take R square, when you take L square, that means if you square the small quantity, so that small quantity when you square, it become much smaller than L. So, or I can say this L square, right, can be neglected compared to R square. So if you neglect this L square, then this B axial becomes how much? Becomes 2 mu naught upon 4 pi m r upon, if you neglect this, then you'll get just R square. So with this square, it becomes R4. Now I cancel this with this 4, you'll get R3 here. So finally, your B axial, it is equals to twice, or I'll write in this way, mu naught upon 4 pi 2m upon r cube. So this is the magnetic field at the axial point of a magnetic dipole or of a bar magnet. Okay, so I'll name this as equation number 3. Alright, so look, this equation, right, it is similar to the electric field at an axial point of an electric dipole, where we have, this is the equation. Right, in an electric dipole, the electric field at an axial point is equals to this much. So similarly, just compare it to, you will see that this magnetic field at an axial point, it is actually almost the same, but the only thing is, in place of this 1 upon 4 pi epsilon naught, we write mu naught upon 4 pi. This factor 2, over there also we have factor 2, and r cubed, here also we have r cubed, and this m, which is the magnetic dipole moment, but here we have electric dipole moment. Okay, alright. Now, where is the directions of this net magnetic field at a point P? So this net magnetic field at a point P, it will be acting along the same direction as the larger force. Okay, if you look at these two forces, Fs and Fn, now you can tell me which force is larger. Definitely Fn is larger than Fs, because this point P, it is closer to the North Pole than to the South Pole. So that means this point P here, that means this unit North Pole will experience more repulsive force than the attractive force. So as a result, my net magnetic field will be along this Fn. So this is about the directions of a magnetic field. Okay, so I hope this is clear, right?